Good morning, dear invitees and delegates. So now we'll have session. So in this session, we have Dr. Raghavendra Pratap Singh as the chair. So he is currently working as Deputy General Manager at the National High Speed Rail Corporation Limited and is a part of team responsible for executing India's first bullet train project, that is from Mumbai to Ahmedabad high speed rail project. He is currently associated with geotechnical investigation and ground strength assessment through pile load tests and plate load tests. He obtained his master's and PhD from IIT Bombay, and I understand he is a student of Professor Deepankar and recipient of Doctoral Research Award during I.I.Sc. 2019 conference and many best paper awards for his publications related with railway research. He has over 19 years of experience working in Indian Railways at various capacities. He was instrumental in developing a world-class geotechnical laboratory at I.R.I.C. in Pune, which was complemented by Niti Aayog. He has undergone various training programs related to the conventional railway and high-speed railway and working with JICA with high-speed railway technology transfer from Japan. I welcome Dr. R.P. Singh for this session for chairing. And we have Dr. Venkataramana working as Assistant Professor in Department of Civil Engineering, NIT Warangal as co-chair for the session. Dr. Ramana worked as Geotechnical Engineer for ground improvement and at Visakhapatnam Airport. And he has been with Hindustan Aeronautics as an engineer at Koraput Division. And he joined Ministry of Water Resources CSMRS as scientist in 2010. He has associated with geotechnical and rock mechanics investigations for various water resources projects and hydropower projects, in particular with reference to landslide studies, foundation investigation for bridges and railways located in India and neighboring countries like Bhutan, Nepal, and Myanmar. He has, to his credit, investigation of more than 40 projects. He published 42 research papers in national and international journals and conferences. He has delivered 25 lectures and prepared more than 60 technical reports. Welcome, Dr. G.V. Ramana as the co-chair for the session. Now I'll hand over the session to the chair and co-chair. Thank you.
Thank you, sir. It is an honor for me to introduce the special lecture by my supervisor, MTech and PhD both, Professor Deepankar Chaudhary. Professor Chaudhary is Professor Tarun Khan, Chair Professor and Head of Civil Engineering Department at IIT Bombay and Adjunct Professor of Academy of Scientific and Innovative Research of CSIR laboratories connected to CSIR CBRI Roorkee of India. Professor Chaudhary has pursued B from Jadavpur University, ME and PhD from I.I.Sc. Bangalore. Professor Chaudhary also worked as visiting fellow faculty at NUS Singapore, University of Wollongong, Australia, UC Berkeley. He is an elected fellow of the oldest Science Academy of India, the National Academy of Sciences. He is an associate editor of I.I.Sc. International Journal of Geomechanics, Indian Geotechnical Journal, Journal of Civil Engineering of Institution of Engineers India, Springer INAE Letters Springer. He serves as editorial board member of Soils and Foundation elsewhere, Canadian Geotechnical Journal, Geotechnical and Geological Engineering, Springer, Geomechanics and Engineering, Techno Press. Professor Chaudhary's major research area are civil, geotechnical, earthquake engineering, computational geomechanics, foundation engineering, soil dynamics. Professor Chaudhary authored over 250 technical publications, including about 140 peer-reviewed journal papers, which are highly cited all over the world. He is the current secretary of Technical Committee TC207, Soil Structure Interaction and Retaining Walls of International Society of Soil Mechanics and Geotechnical Engineering, and former secretary of TC212, D Foundation of ISSMG, in addition to present and former member of TC203 and editorial board member of ISSMG Bulletin. So with this brief introduction, I would like to request Professor Chaudhary to give a lecture on the topic. Yeah, please, Professor Chaudhary.
So, namaskar, everybody. So, thank you, Dr. R.P. Singh and Dr. G.V. Ramana for chairing this session. And I am more delighted to see that one of my former PhD research scholar is chairing this session. I'm very happy. Thanks for your kind words in introducing. And also thanks to all the organizers for having me over here for this lecture of SOAP for 7 ICRAG conference. So today I'm going to talk about a topic I have chosen, which is, I will say, not regular topics which I typically discuss on foundations. This is also related to foundation, but not only due to the earthquake, though the conference is mainly on earthquake, but I have chosen a topic of recent relevance on which several projects in India are going on, and I'm sure at various places in the world as well. And we were fortunate to be participating in some of the real-time project on this. So controlled ground-borne vibrations for design of substructural systems, which includes the foundations, as I mentioned, the theory and practice. This is the topic I have chosen for today's lecture. And for this work, my co-author is my another former PhD scholar, Dr. Milind Patil, who is currently a senior geotechnical engineer in AFRI India Private Limited. And other researchers who are involved or who were involved on this topic in our Geotechnical Earthquake Engineering Laboratory of IIT Bombay are shown over here. Dr. Milind Patil, as I already mentioned, he is a co-author of this paper for the conference. And Dr. Jaikumar Shukla, he also participated in one of the project. And Mr. Ritik Nandi, he also worked on one of the project. And Ms. Tulika Bose, who also worked on one of the theoretical aspects. These are various industry and organizing partners, like through whom we got the projects or handle the projects for them as an expert, like Geodynamics, then for Delhi Metro Railway Corporation Limited, or DMRC in short, what we call. Then the German Academic Exchange Service, they funded a collaborative project to support the Tulika Bose work from DAD, and the ACOM, for ACOM, another project we did at the site for the expert advice to provide in such problem. If we try to introduce the topic, like we all know that this ground-borne vibration, it is propagated in the waveform in the ground, and it can be transmitted into foundations of nearby buildings. And that is how it is like concerned many a times, that whether our existing building, which probably was not designed to incorporate those additional ground-borne vibration, whether our building will collapse or crack, or some problem will occur in the existing building or not. So vibrations generated from construction activities of rail and road traffic system that may disturb the stability of the old, especially the heritage structure, which is, of course, we know the value of the heritage structures, and I will show in one of the project how relevant it was. Then also the geomechanical problems which are associated with such kind of vibrations that can be solved by analyzing the soil structure interaction problem as a whole using either analytical method or numerical methods. So these ground-borne vibration, as I mentioned, it can come from the construction activity, it can come from the various train movement, vehicular traffic movement, etc., which need to be checked, and also the seismic activity, of course, it is there. So first, I would like to highlight the theoretical work, what has been done in our laboratory. Of course, there are several researchers worldwide who worked on this topic, but from IIT Bombay, we tried to work on this area and analytical and numerically. So that was, this is the paper. One can see the details in Journal of Geotechnical and Geoenvironmental Engineering in 2018 I.I.Sc, a work of Tulika. in collaboration with our lab and the RWTH Aachen lab, because it was under the DAD exchange program and research project. So if you see what we essentially we tried to find out over here, if you have an existing structure, what is the mitigation of that ground-borne vibration which is coming from your future construction or harmonic load or machine-induced load or the future railway line, etc. So here Tulika, she studied the aspect of providing an open trench and infill trench, both this condition, how that helps in reducing this kind of ground-borne vibrations on the existing foundations. So essentially, if you see over here that this is the mitigation technique what has been proposed, which is nothing but an vibration isolation in terms of infill trench or the open trench. Now, how they perform that she has actually checked along with the case of German train, you know, Deutsche Bahn, they have ICE, which is called um, that is the highest speed train in Germany. So this is the result of variation in average amplitude reduction ratio with the shear wave velocity of the fill material and in situ soil. If you see on the left hand side results, this essentially shows the average amplitude reduction ratio with respect to the shear wave velocity ratio. And the right side, this bottom results, it shows how that normalized depth of that trench that actually helps in reducing this amplitude reduction. And just to talk about the mitigation of ground-borne vibration further in terms of the train movement. So this is the IC train, as I have mentioned. So essentially, she took the velocity of the train like 80 kilometer per hour, 180 kilometer per hour, and 250 kilometer per hour. So this 250 kilometer per hour is a typical kind of, I will say, on a highest band of speed which this IC runs in Germany. So this, how it creates the particle movement or what we call peak particle velocity that has been obtained. If you see that, it is obviously known that if you go away from the face of the foundation and if you go away from the face of the train or where the vibration gets created, obviously that peak particle velocity gets reduced. So this is what you can see, the reduction in the PPV or peak particle velocity with different velocity of the train of IC, what she has studied in her work. And this in absence of trench. First of all, this is in absence of trench when no remediation has been considered. And this is based on different speed of the train are shown over here. This slide, it shows essentially how in frequency values changes in comparison with trench and without trench. That means with no isolation technique and with isolation technique for three different train speed. One is 180 kilometer per hour and this is 250 kilometer per hour. This is how you can say obviously there is an significant reduction in the PPV value when one use such isolation technique like trench. So after this theoretical knowledge, we executed two real life project, important project of national importance. The first project of case study I want to highlight over here, our duty or our advice expert as was asked, that was for the archaeological impact assessment study due to the vibration and for heritage structures of New Delhi region for the proposed Delhi Metro, in short we call DMRC extension line. This is the line 4, the new line which is coming up. As we know, till now Delhi Metro has three line 1, 2 and 3 phases essentially, not 3 lines, 3 phases. And now the 4th phase is coming. So, involved geotechnical consultant was geodynamics, And for expert advice, IIT Bombay was contacted and we contributed for this work. Those who are aware about, for my international colleague or participants who are present, if any, that Delhi Metro is the largest and busiest metro at present in India. And in world, it is 8th longest metro system as of now, and 16th largest by the number of riders or commuters. The network consists of 8 colored coded regular lines, 8 lines, running for 377 kilometers and serving 274 stations. And the system has a mix of underground portion, at grade portion, and at elevated stations also. So essentially, the new phase, which is proposed phase 4, this is the route. So this is the map of India. This is Delhi, and I'm expanding over here. You can see this is the Google map. This red color alignment was the old alignment. Now there are several reasons why DMRC came up, because Archaeological Society of India, there are stringent constraints that one should not construct any new thing nearby an existing archaeological structure within 100-meter distance. So considering that, the new alignment has been proposed like this. But even though the new alignment has been proposed or revised, still the locality is such that it is highly populated area, first of all, and also high number of heritage structures are there. You can see all these star marks actually are various heritage structure, and that should not get damaged because of the construction or planning of this new metro. So this is, as I said, phase 4 of proposed metro line of DMRC, and these are various heritage structure you can see with this pink color hashed portions at various location, and this is the line segment. This is the proposed line. And in this line, what was proposed, or what is proposed essentially, this will be underground metro, and this portion where there is a blue color line, you can see this is the station portion called Mehrauli. So Mehrauli station is the station portion where the station will be 15 meters below the ground. So that is what is proposed. So our work or our duty or our assignment was to provide an expert advice that whether, because of the construction of this new metro line, whether there will be any sort of damage on these various heritage structure due to this ground-borne vibration. But remember, this ground-borne vibration is, there can be several causes of that when we are considering a metro line like this. So as I mentioned, that phase 4 of Delhi Metro, it consists of 103 kilometer length, and the present site is Mehrauli subway station that has been proposed, that is connecting the Tughlakabad and the Delhi Aerocity, these two places. Then Mehrauli station is to be constructed with cut and covered tunnel of 270 meter versus 17 meter, and connected to 2 twin tunnel system of 6.35 meter diameter. The new alignment of proposed metro is passing by few heritage sites, as I already mentioned. So impact assessment of these heritage sites has been carried out for possible construction activities. That is, what are the things which can create ground-borne vibration? As I was mentioning, it is not only one source. It can be due to the excavation, it can be due to the tunneling, or it can be due to the drilling or blasting activities in addition to the movement of the train. So these are the structures, heritage structures. 7 heritage structures has been identified in the close vicinity. You can see Bhul Bhulaiya, Gandhak Ki Bauli, Rajan Ki Bauli, Tomb of Balban, Jamali Kamali Tomb, Azam Khan's tomb, and the most historical monumental structure, that is Qutub Minar, which all of our international guests also know about it. So these were built in during this time. You can see very old structures. their latitude, longitude, all are given over here. And this is what is important for us, that is how much is the distance of these structures, heritage structure, from that proposed metro alignment line. So you can see this Gandhak Ki Baoli is the closest one, 41 meter. And the next one is Rajan Ki Baoli, 78 meter. And Qutub Minar is about 300 meter away from that line. So what are the activities during the ground vibration and transmission? You can see these are the things which creates the ground borne vibration, for which we have to find out the stability or the suitability of the foundation system. So foundation piling, drilling and blasting, chiseling and excavation, then tunnel through tunnel boring machine, and other construction works. And what are the factors which influence the damage to the structure, like duration of vibration, state of stress, energy per blow or per cycle, distance between the source and the receiver, and the characteristics of the structure, and soil profile, of course. So what is the geotechnical condition at the site? Actually, if you see, the site location falls near the Indo-Gangetic plain alluvial deposit that are composed of gravelly, sandy, silty, and clay, to some extent a field material, and then come fissured rock or weathered rock. Actually, remains in the some organic matters are also present. So tunnel depth is about 15 meters from the ground surface, and tunnel is passing through highly weathered rock layer, as I said, the VS value ranging between 400 to 600 meters per second. If you see, these are the structures, these pictures taken by me and Dr. Jay Shukla when we went for the site visit to identify what are the existing damages in the building, so that later on people should not point out that, okay, because of the metro rail, these damages have happened. So what is the existing damage, existing condition of these heritage structures, all has been taken, and that has been actually, this report finally the DMRC submitted to Archaeological Society of India also, so that they can also go through this and approve the planning. This is Azam Khan's tomb, Jamali Kamali. This is, of course, the Qutub Minar, which is little far away, as I said, 300 meters. So this picture I have taken from a rock crop at this location where I was standing and taking this picture. And so soil deposit in this site, you can see typically about 5 to 12 meters. So that is the typical overburdened soil, followed by that weak rock. An effect of ground-borne vibration due to the construction activity on heritage structure has been assessed, and we have used the three-dimensional finite element analysis in Plaxis 3D to find out what happens to that Mehroli station location first due to this excavation-induced settlement. So this is that Mehroli station location, and this is the entire metro, underground metro alignment in the Delhi Metro Phase 4. This is as per the codal provision. First, we checked all the codal provision. And if you remember, it is not only that for such important project, we have to stick to our Indian code. Indian code, of course, has to be checked. But in addition to that, what we did, we have verified the various other international well-renowned codes which are actually used for international projects as well, so that it increases the confidence level. So the vibration, as I said, in terms of peak particle velocity, what we always measure. So you can see this is as per the BS code. You can see that the distance from the source of the excitation, what I mentioned, these are the structures where they are located actually. So you can see that this actually the PPB value is quite low or close to nil. This is another activity, that is piles drilled through the dense granular or sandy stratum or weathered rock. You can see the same structures. The nearest structures, of course, we have taken, as I said, which is like 41 meters, 78 meter, and so on. You can see here also the limit of PPB is very low as per that BS code. We have also used the DIN code, the German code. The German code actually they use for the IC and related impact design. So for heritage structure, if you see the maximum allowed PPB is 2 millimeter per second, whereas in our case, we found from this codal provision, it is coming close to just 0.1 millimeter per second. So which is very low. And these are the various distance and it depends on the frequency. Remember, as you know, this ground-borne vibration, that at what frequency your source or input actually working, whether 10 hertz, 20 hertz, 30 hertz, these are the typical values which we mentioned over here. Next one, we have to check when the tunneling is working or tunnel work is going on. Due to that tunnel work, what is that induced vibration as per the BS code? And you can see here the PPV value is bit higher. It is not that low as what we have seen the excavation time. So this is the tunneling work, and Gandhak Ki Baoli, then Rajan Ki Baoli. These are the two nearest closest to the proposed line, as I have already mentioned. You can see there is a kind of significant amount, about 1.5 millimeter per second of PPV value. So these are the values you can see for all the 7 heritage structures we have found out. That is the distance, their PPV value, existing traffic, vibration exposure, that also we measured, because what is the existing vibration that creates because of the present condition, whatever vehicular movement in that region is there. And then total PPV value. So me and Dr. Jayakumar Shukla actually went to the site and actually obtained all these values. Then coming to the safe distance for the blasting action, it is a controlled blasting, because in the weathered rock, when they are constructing or proposing the construction of the station at a depth of 15 meter, at various phases of each of 3 meter, they proposed in 5 phases, the construction will be done. So what is that as per our Indian standard code of blasting, how much blast charge is allowed in such distance for all these heritage structure, that also we have calculated. Then we carried out the Flaxis 3D, three-dimensional finite element analysis for the Mehrauli metro station, which is at a 15 meter depth, as I have mentioned, with 2 twin tunnels going at 6.35 meter diameter. And this is the influence zone or the displacement contours is affecting the Mehrauli station. And this is the cross-sectional view. You can see the Rajan Ki Baoli is one of the nearest, and Qutub Minar is far away. So it is not even coming in the influence zone as far as this ground-borne vibration is concerned. These are various plastic points for the excavation. This is, as I said, phase-wise excavation was proposed in 5 phases for the Mehrauli station, and how much it affects the total displacement on all these existing heritage structure, that actually we have computed. Then also 2-dimensional analysis has been carried out in terms of tunnel work, like when tunnel boring machine is moving in the entire stretch of the metro tunnel, how much disturbance or ground-borne vibration it is creating, that also we checked. You can see this is the influence zone, and these are the locations of the nearest structures, heritage structures, for various conditions of whether single tunnel first constructed, left side or right side. So all the options we have given, that is which becomes the critical one, and 2 tunnels, etc. So you can see this is tunnel induced surface subsidence, which is shown over here in this top picture. You can see, and due to the construction of twin tunnel, and this is what effective principal stress, how it changes. The third thing we have to check, remember, not only all these vibrations due to the ground-borne vibration, but also due to the seismic effect, because let us not forget the zone, Delhi is in seismic zone 4, as we all know, as per Indian code, seismic zonation code. So we have to check whether under that zone 4 also this activity of underground tunneling and its effect on the what is called nearby heritage structures, how much it is there or not. So finally, these are the actually the degree of damage you can see, and the corresponding details with limiting strain. And this is what we have finally recommended to them, that what they should do, like parameters to be monitored at construction phase, and at different phases, maybe the nearby location structure, it has to be monitored, and the frequency has to be also maintained as we have proposed over here. So as I said, typically 40 meter to 100 meter, those heritage structures, we found that their threshold limit of PPV is less than the proposed value of 2 millimeter per second, so which is safe. And that's why we have suggested with those recommendations, they can go ahead with this construction. Now, I will, because of lack of time, I will quickly go to the second project which we executed recently. This is in Mumbai. So this is in Mumbai. You can see here, actually, as you all know, the bullet train is now, the project is going on in full phase. Actually, I'm happy that Dr. R.P. Singh is here as a chairman for this session. He is deeply involved in this project of bullet train, Mumbai Ahmedabad bullet train. So we got this project through AECOM, that we have been asked to provide expert. There is a data center building which is in Ghansoli, Navi Mumbai area in Maharashtra, and which is very close to this bullet train site. And they are very worried about, because data center, as you know, several systems, computers, everything will be there. So building dimension is about 46-meter height and plan dimension 85 and 45 meter. You can see that 25-meter is the distance of this building of data center from the proposed bullet train segmental line. So we have been asked to check whether it creates the damage to the data center building and foundation system and overall entire structure. So here also we have checked all the conditions like bullet train operations, and also while construction, the tunnel boring machine operations also, how much it affects, as well as the seismic operations. So here again, we have checked the design code provisions first, and then we have executed the numerical analysis also for this project. That is how much magnitude of that ground vibrations is coming in terms of PPV. So here again, the first we checked with the codal provisions, as I said, not only the Indian code, but also all important international code. Like first DIN code, you can see the reference value of equivalence PPV for various constructions is mentioned over here. Like this is for 30 mm per second for this well-reinforced buildings, etc. And where buildings not corresponding to up to this above this thing. So for security purpose and data center building, I will say restrictions, etc., they try to go for actually the lower value. This is as per DIN. Again, I mentioned it is highly dependent on the frequency of your dynamic loading. So at what frequency ranges all these values of actually this changes the PPB value, you can see that buildings used for commercial purpose, industrial building, and all those details are given in this code. This is the Swiss code. Switzerland, actually, they use this code for such bullet train construction and associated ground. You can see AMS is essentially, AMS stands for machine, traffic, and constructional equipment related thing, and S related to the blasting. So here also they have given a range of the frequency, and for that corresponding what are the limiting value of that peak particle velocity for various conditions of building. Australian standard, the Australian standard also, you can see that, like they say historical building, it is 2 mm per second, which essentially our IS code also mentions. So essentially this we have used, as I have shown in the Delhi Metro project. So this Australian standard also gives, depending on the rise of the building and condition of the building and utility of the building, what is the value of the PPV. And here the subsurface soil profiling was given to us, the SPT values at 10 borehole locations. These are the typical layers, like initial about half a meter about fill material, then half to about 2.5 meter is withered rock, and then good quality basalt rock is available. As somebody is aware about the Mumbai region ground profiling, they will be knowing this. So now TBM related induced vibration, how much it affects in terms of PPV. This is chart of Hiller, which is equivalent to what we typically teach in soil dynamics course, the Richards chart for machine foundation, of course. But this is a kind of equivalence, I can say, that TBM induced for different types of soil, how much disturbance it creates for like to human being, to structures, to it is noticeable, non-noticeable, blasting, and when it goes to complete damage and so on. Now, this also we have checked whether it is satisfying that criteria or not. So this is the tunnel location, and this is the DC building you can see, and this is the distance 25 meter and depth is 20 meter is proposed for this bullet train site. And this is what mechanized tunnel boring, this is in first method we have adopted, and accordingly you can see the PPV value coming about close to 2 millimeter per second, which is still within the limit actually. This is another method, Hiller and Krebs method. We have used actually the source of construction induced vibration, essentially how it affects the foundation system, and how the shear wave velocity of the soil and the frequency is important, and the damping factor of the soil is important. That has been shown. These are various values of PPV depending on the distance from the tunnel site or tunnel face. You can see the third one. Whenever you do such kind of vibration analysis, ground-borne vibration, we have should not forget to check whether the seismically also the site is actually compatible or not. So that seismic study also we did. As we all know, the Mumbai comes under zone 3 as per IS code. So for zone 3 factor, we have found out the equivalence of the dynamic load and how it affects the influence zone essentially for that tunnel area. This is the tunnel location and this is the building area. So how much it creates the effect on the surrounding structure. So with this, our final recommendation for this project was like ground-borne vibrations at foundation level of that center building due to the construction of bullet train and operation are within the permissible limit as suggested by several codal provisions, as well as we have done the numerical analysis also, and we have shown that. So structural damage or in worst case collapse of the tunnel will not affect any structural stability issues on the serviceability of that data center building. So with this, I have come to the end of my presentation. Dhanyabad. Thank you all for coming to my lecture. Namaskar. If there are any queries, I would like to answer. Thank you so much.
Thank you, sir. And there is one question from Mrs. Mehbooba Ahmed. Dear sir, what is about the boundary condition used in lateral and bottom boundary in different numerical model, that is Plexus 2D and 3D model?
Yeah, I think what she's asking essentially, the boundary condition depending on like what structure you are modeling first of all, and what is the domain and distance you are considering. So typically we consider, as we know, the bottom generally consider we as a fixed, and the surrounding side we consider as a roller. So that is the typical boundary conditions taken in the Plexus model. But remember, we always should take a distance such that first of all, that distance should be beyond your influence zone, much beyond actually. We generally take 3B to 5B times. And depending on structure again, that sensitivity study or the analysis has to be done, how much distance you are keeping for boundary. And another thing you have to see, when you are doing any dynamic analysis, what is the meshing size and corresponding boundary distance, so that you don't miss out what is called crest and trough portion each cycle of a load, equivalence load of dynamic load from that meshing consideration. Yeah.
So next question, it is not a question, it is just a statement. I think it is from Harsha. It is good to hear yet another interesting lecture from you. In general, during TBM excavation, the ground vibrations are directly related to penetration rate of the TBM machine and tunnel face stability.
Yeah. So thank you for your comment, and yes, I agree. Yes, all this criteria has been taken. Yeah.
Thanks, sir, for a very informative lecture. And as we know, these days metros are coming in almost every cities. Every state capital, there is a metro proposal. And at present, more than 50 PSUs of railways are there, and in each PSU there is some metro related, underground related work. So this study will be very helpful in all the metro projects, railway projects, to assess whether the existing structures are safe, or what will be the effect of the tunneling activities on the stability and the safety of the building, and the vice versa, whether the tunnel will be safe due to the existence of the high-rise building. As we know, in Mumbai, there are many high-rise building in the alignment of the bullet train and as well as in the alignment of Metro Package 3. So this study will give the confidence to the client about the safety of the structures as well as the safety of the high-speed or metro rail projects. So thank you very much, sir, for this informative lecture.
Thank you.
Thank you, sir. Ramana, sir, you want to say something?
Yes, sir. Very nice presentation, sir. I learned many things. Thank you very much, sir. And sir,
Thank
only
you.
one small information I need, sir. So, what are the nowadays best instruments to measure the peak particle velocity, sir?
Yeah, so essentially we find the equivalence, as you know, from the what is called field monitored vibration level. We find out the equivalence of that in terms of the loading. See, essentially you have to equivalence of load also you have to see. When you are talking the peak particle velocity, I will not say it is a direct measurement. It is an indirect measurement. So depending on how equivalence of the dynamic load you are making, correspondingly, you can always find out the peak particle velocity. Yeah.
Thank you very much, sir.
Now I will request Mr. Pranjal, numerical study of dynamic loading on ballastless railway tracks. So now you can share your screen and start your presentation.
Welcome all. My presentation, the topic of my presentation is the numerical study of dynamic loading on ballastless rail track. So actually, I am currently doing my PhD in IIT Delhi. This work which I have done, I'm going to present in my PPT. I have done it in my master's in IIT Kanpur. So let us just start with the outline. The basic outline will be introduction, literature survey, the FEM modeling, and we'll finalize it with the results and conclusions. So just go into the introduction. Basically, there is a discussion of moving to ballastless track from ballasted tracks, which we traditionally use, and there are positive points and negative points of both of them. So in India, we are trying to use ballastless tracks in metros and several structures like one of them is in Pir Panjal Tunnel in J&K, and some parts of Konkan Railway are specifically built with ballastless track because of the condition there. Which cannot have very much vibrational loads. So this is a basic diagram of a ballasted and ballastless track. So in traditional ballasted track, we have ballast, subgrade, which are the granular layers. In ballastless track, we remove this granular layer using like continuous asphalt or concrete layer. Hydraulically bonded layer is also a cementitious layer. Frost protection layer we generally use in normally this model comes from Nordic countries like Germany and Sweden. So their frost protection layer is used, but in India we don't have to use it. So this is a basic diagram. Basically granular to continuous layers, we switch from ballasted to ballastless. Now we have these differences like maintenance cost and construction cost and everything. But let me tell you in short that with the life cycle, the actual cost of building ballastless track becomes lower than the actual ballasted track, because the maintenance cost of ballasted tracks becomes higher with general life cycle of 20 years. So after 20 years, the cost actually cuts, like the cost becomes equal, and after that ballastless track becomes cheaper than the ballasted ones. So let me just go ahead. Generally, we try to deal the model with just a numerical model, where we used earlier in our literature study that we can use Euler-Bernoulli beam equation, basically beam on elastic foundation, and solve the general mathematical equation of moving load on various layers. And this work has been done by various researchers, specifically Malik et al. And there are, from my literature survey, I have seen that there are experimental analysis where people have measured this vibration as told by Dipankar Chaudhary sir. basically using vibration of the ground when the rail passes. There it can also be done. It is shown in Jorlings. And software simulation validated with the lab model is done by various people like Soumya et al. And Mikas. So they have their combined work. So my problem statement basically is to design a rail track which can be used for like Indian conditions. So I started it from the radar model. So radar model basically is a model where we have sleepers or whatever blocks which are carrying the rails encased in CBL layer. So CBL layer is equivalent to the ballast layer in ballastless rail track case. And I basically in India we generally go with the model where we don't try to embed the sleepers into CBL, but we first build the CBL and then put the sleepers over it. So there are two models which are analyzed, but we'll look into one of them. So in FEM modeling, we first validated our model with the Mikas study, which dealt with the static load analysis. But we have, in the authors of this research have concentrated their research on moving load analysis, or specifically G-track type of model. So this is the snapshot of Abacus model. Actually, we have used the symmetry of model, but it is for the showing purpose that this kind of wheel motion will be occurring on a rail track, where we have rail placed over sleeper and sleeper are placed over CBL and hydraulically bonded layer. And finally, we have just omitted the FPL and we directly use the like subgrade layer there. And the wheel axle assembly is actually loaded by 10 kilonewton at each wheel, so 200 kilonewton as a combined load, and then the load is moved at various speeds. Basically, it's the sliding. This wheel is slided as you can see at various speeds. So we'll see the results. These are the material properties. These material properties are generally elastic properties that which are presented here. So we actually use the static general procedure to load, and then later on dynamic implicit. Static procedures generally don't take account of mass matrix and damping. However, while we started the load motion, we use dynamic implicit, which takes account of mass matrix kind of damping as well as damping. So this is a better procedure while we move the load, and we actually move the load to 100 meter and for various times. Basically, changing the time will change the speed for a specific distance. So that's how we change the control the speed of motion. Now the results are presented as the validation and moving load model. So let me just go ahead into the results. So first, the validation of procedure is done with the one by Mikas. So the blue line, as you can see here, not the blue, sorry, black dashed line. The results are very similar to the Mikas's, and this black dashed line is in our model represented by when we created rail as Euler-Bernoulli beam with a spring dashpot as support instead of just tie contact. Tie contact basically means that we will not have any stiffness at the contact of a rail and sleeper, but spring dashpot suggests that we have a like a rubber-like contact where it has some damping and stiffness as well. So spring dashpot type of contact. So based on this, we can see that this Euler-Bernoulli beam with spring dashpot validates with the Mikas's model. But however, due to our nature of realism in Abacus, so like FEM, so we use the blue dotted line that is rail on 3D solid part and tie contact for our actual model. So, sorry. So here you can see the results of moving load. The initial this line which you are seeing here is actually like one by frame by frame. These plots are presented, and you can see with the moving load like at 30 mm from the starting point of the motion. The like we haven't moved anything, so the deflection is about 2 millimeter. And then as we started moving, because once we started moving, we again started applying load from 0 to the highest value, that is 100 kilonewton at each wheel. So this the vertical deflection actually started coming down, and then it started increasing again towards the finishing of the motion. And at the finish, we'll see that we have some vertical deflection. But however, this plots are the like basis of what came after this, what will come after this. So finally, we measured the maximum downward deflection and maximum uplift, which are the like peak and minima and maximum of these plots. So based of this, we get this plot that with increasing speed, these are the plots of speed versus maximum downward deflection and maximum uplift. So uplift generally is not considered a good thing to measure, because in rail tracks, these are
Please
like
conclude.
yeah. So basically, we can see that with increasing speed, we have a switch from subcritical to supercritical speeds. At critical speed, we have the maximum vibration, and supercritical speeds we have like it's very similar to resonance, and that's what we have concluded from this, that for a track very similar to one which is analyzed in this research, the critical speed comes between the values of 150 to 200 kilometer per hour, and there is a like a lag distance phenomena which parameter which is almost zero at critical speed, and after passing from subcritical to supercritical, the lag distance become like negative to positive. So that's what we concluded from our research. So these are the selected references. Thank you.
I think any questions from the audience, sir? There is no any chat box. Okay, sir. Okay.
There is no,
Yeah, one question, very short question. So
Yes, sir.
what is so how can we prevent that vibration effect actually, for example, in respect of ballast and without ballast?
So actually, from the literature of it was not presented here due to limitation of the thing, but the literature presented by Mikas, he actually uh, from which we also validated it, shows that the ballastless tracks absorb more vibration using the elastic pads, which can be like instead of in ballastless track we use the granular layer which is ballast, so it absorbs the vibrations because of the higher deformation. But in ballastless track we use the rubber pads to absorb those vibrations under the sleepers.
So is there any material testing for that one? How much observation energy it can absorb?
Sorry, sir, I couldn't hear you.
Yeah, that elastic pads, whatever you have used, so have certain basic tests?
Yeah, so, not exactly the test, but there have been model testing, not a material testing, but a model testing by comparing the rail track with and without using the elastic pad. So there are several what should I say, Chinese papers from CRT3, which is Chinese rail track, high speed rail track 3. There have been several research on this, and they have concluded that using elastic pads in any form will be beneficial instead of not using them. So and there are research from Germany as well, so it's good to use them
I think.
to reduce the vibration.
Okay, sir. I think if there is no questions,
yeah. So
sir, we can
just
proceed.
Pranjal, one thing for information, in both the whether it is ballastless or ballasted, a rubber pad is the essential part. In both the cases, rubber pads are there, the elastic
Yes.
pads below the rail seats.
Yes, sir.
Okay, it is not it is in only one type. Both the cases it is there. And second, one thing is the settlement limits. In ballastless track, it is very stringent, whereas in ballasted track, we allow certain degree of settlement, maybe up to 7 mm or 10 mm, like that. So it is also one thing that you can include in your part. Yeah.
Okay.
So thank you, Pranjal.
Thank you.
Next speaker is Rohan. The topic is analysis of urban tunnels under different loading conditions. So,
Yeah.
Rohan
Yes.
Jahamne is from IIT Delhi. Yeah. So yes,
Yes, sir.
is yours. You can start.
Good afternoon to all of you. Today, I'm going to present one of my research topic, analysis of urban tunnels under different loading conditions. So I'm an MTech student from IIT Delhi, and this is one of my research work, which I'm going to present in front of you guys. So first, we look upon the outline, like what are the structures which are currently there in the soft and weather rocks. then problems associated with that rocks, then static loading, dynamic loading, and to validate that particular experimental modeling conditions on small scale, how I have validated with the numerical modeling approach. So as most of you guys knows that large deformation in the underground structure at shallow depth has always been a threat to engineering safety in the process of tunnel construction, especially when that tunnel has crosses, very highly induced stress area, which we call it as a which we can take it as the example of joints or fracture zone and weather or soft rocks. So these are the structures which are currently there on soft rocks, which has been constructed and facing the same problem which I am talking about. So large deformation occurs in the rock mass. It totally depends. It totally depends upon the basic engineering properties, which we mostly elaborate through the laboratory work, that are the uniaxial compressive strength, then water softening, aerological characteristic, etc., etc. So the basic objective of any design engineer is to is to determine the stress concentration in that particular rock mass. And how is going to determine the stress concentration? So by creating a stress field, as a uniformly distributed, so he can clearly optimize his support system as well. So these are the different structures which are currently there in the soft and weather rocks, like northern route of cities in Pakistan, border tunnel in between the Argentina and Chile, road to Vidraru Lake, Romania, then A3 highway, Italy, then Bir Panjal railway tunnel in Jammu, Chenab Bridge in Jammu, and Narsi Chenani highway tunnels. So more than 5,000 projects of highway, railways, and bridge abutments are completed in this particular kind of area where soft and weather rock kind of geologies occur, where it is very difficult to progress that tunnel. So as most of you guys knows that there are some kind of problems are there while constructing our tunnel in soft and weather rocks, like because of its low strength, which lies in the range of 1 to 25 megapascal, and then the deformability issues are very large, strong dependence on degree of saturation or temperature. Then this kind of structures are very susceptible to alteration. Then uneven stresses to the lining at very low strain rate. So there are different kind of loading conditions which are finally analyzed on my urban metro tunnels, which occur at very shallow depth. So first is the static loading, and then quasi-static or dynamic loading. So as most of you know, the static loading condition, the strain rate is ranging from 0 to 0.1, and then in dynamic it ranges from 0.1 to 10,000. So these are the types of structures which are there in kind of this loading conditions. So actually, to validate these structures with the prototype kind of modeling, mostly as you can see here in the screen. So there are missile attacks, occur by terrorist activities or any other kind of organization through which it impacted on our underground metro tunnels or any kind of subway structures which occurs at shallow depth, and it occurs, and the result is you can see here that tunnel is totally or completely destroyed. So to safeguard this structure and to continue or to proceed any kind of experimental investigation in practical structures or in real life structure, it is very tedious and costly process. We cannot complete, or we cannot continue our experimental study in practical purpose. So to simulate this kind of structure, so we have created one small scale model through experimental investigation, and we have validated it with the numerical modeling by means of I.I.Sc version 6.4, and we validate it completely by selecting a different kind of material properties. So I will come through that also. And by using scaling law, we reduce the dimensions of that particular structure in a small scale model. As I discussed with you, that it is very expensive to carry out field tests for impact or blast resistance underground structures. Skill level is also required. So a simple approach of physical modeling would be useful for a preliminary design and parametric studies. So as most of you guys right now facing a problem or have a doubt in mind that how we going to model the geomaterials under impact loading. So by keeping different kind of structures and different kind of material properties, I have made one geomaterial which consists of different kind of materials and have different kind of specifications and proportions. So I have selected this kind of materials like plaster of Paris by taking 50% of its weightage, sand, clay like kaolin clay, mica, and water by cement ratio. I have kept it as 0.6. So yeah, so you can clearly visible here the four materials which I have chosen while creating a geomaterial: plaster of Paris, kaolin clay, Badarpur sand, and mica flakes. And these are the engineering properties which I evaluated through it through different kind of laboratory testing, like from uniaxial compressive strength testing, interaxial testing. I have utilized, I have come up with the CN5 of that particular geomaterial. So yeah, so to validate that particular project, once the small scale modeling has been validated with the experimental, so we can clearly validate it with the prototype model. So to validate it with the prototype model, so we have selected one project called T48 Tunnel Udhampur Srinagar Baramulla. It's all specification, all locations, all material characterizations are there. Yeah, so here I have present one scenario where to validate our physical experimental model with the field one, we can clearly take its proportion, like from by dividing the modulus of lining by modulus of rock to the modulus of lining by modulus of rock of field. So if the proportion will be same, then we can optimally, or we can clearly taken its proportion to validate it with the experimental study. So this is the Udhampur Srinagar Balamulla T48 tunnel, for which I have taken its parametrical study. So this is the impact testing facility which is currently available in Geotechnical lab of I.I.T Delhi. You can clearly see its impact loading unit. Here I have clearly visible you guys that here's a drop hammer. It is a cylindrical hemispherical nose which is of diameter 5 centimeter, and it is purely of steel. So I have used it for you to use as a drop hammer. So on above that there is an impact testing unit through which we can put a disc weights to take the effect of different loading conditions. And for my modeling, I have taken 3 cover depths. Like here you can clearly see its experimental study, which I have done it through impact testing facility. So I have made a model of geomaterial and take a different cover depths, like from 25 mm to 50 mm.
Please conclude, Mr. Rohan.
Yes, by using scaling law, I have just degraded its dimension to validate it with the experimental one, and to validate it with the numerical one, I have used Abacus 6.4 version to validate it with the numerical model. Use different meshing techniques, mesh conversion study I have performed. So here we can clearly see its comparison between the yield zone in the failed rock tunnel of experimental and numerical. So we can clearly see how we can minimize the error in the experimental as well as numerical. So mostly the results are very close. You can see the length of the crack zone along the tunnel axis in experimental is 97 mm, numerical it is clearly 100 mm. So the error is it's quite low. So there are two curves like load displacement curve and energy displacement curves, which defines the validation between the numerical and experimental study. So the conclusion of my part is the depth of the overburden is very crucial, very critical parameter in quantification of the fracture threshold. Tunnel follows Gaussian distribution along the length. As you can see, the Gaussian distribution curve it follows. In the lower part, the maximum deformation is occur. I think there are 3 cover depths like 25, 35, and 50 mm. So in the low cover depth of 25 mm, mostly the deformation has been very high, and the tunnel follows. And observe that the surrounding material is failing shear and failed surface has been elliptical shape at the top of the tunnel, as you can see in the present graph. So thank you guys for hearing my presentation throughout this session. Thank you very much.
Yeah, Professor.
Sir, I think there is no questions from any participant, sir. I think one question, quick question. See, I think your study, what is the difference between, for example, the energy interaction, maybe energy absorption between the soft and the weathered rock? Which one is more effective? And what is the difference between soft and weathered rock?
Yeah, so actually, as I have told you, sir, that the soft and weathered rock mostly are depend upon the UCS, which we have evaluated through the laboratory. But the most affected rock is mostly the weathered rock, because it, by time it degrades because of the physical and chemical weathering. So yeah, so in both the cases, mostly we have taken this study. We have cover up our experimental study and analyzed that the weathered rock is more crucial than the soft rock at low cover depth, mostly at 25 mm cover depth, which we identified the most deformation has been occur at that cover depth if we have taken the weathered rock in our active scenario.
So what boundary conditions you have applied at the time of modeling?
Boundary condition which I
For
have applied,
especially weathered rock.
especially on the weathered rock, I have put a hinge support in the bottom of the metal boundary, and in the two corners, in the two vertical directions, I have applied the roller support. So I have taken
just listen. My particular question is, so that weathering, whatever weathered rock, na, okay.
Yes.
So how you have actually addressed in the modeling?
I have used its material properties to define the weathered rock while doing the numerical modeling on Abacus by selecting its different properties.
Give me one example of weathered rock. What particular weathered rock actually have occurred in the particular any in-field point of view?
I have taken a phylitic quartzite, which I have taken from
Pilot rock, okay, pilot's rock mass.
Yes.
And even sometimes, so for example, if there is a hard rock is there, even granite also sometimes there is a weathered, na?
Yes.
So how can you address that particular weather in terms of modeling point of view? So that is crucial for your under study. So please address that one properly further.
Okay, sir. Okay, I will surely address it. Sure.
So any more questions, sir, from Ravi sir? Maybe.
Thank you. Thank you, Rohan.
Yes, sir. Thank you.
Excuse me, Mr. Chair and co-chair, a small announcement.
Sir.
Yeah, I think our delegates are not able to pose their question answers. All the delegates, those who want to pose their question answers, you need to minimize your full screen mode. So you have to come out of the full screen mode, then you can find an option to pose question answers. There is a Q&A icon below the screen once you minimize the full screen mode. Okay, thank you, Chairman and Co-Chairman. Thank you very much.
Thank you, sir, for the announcement, and I think we will get more questions. Next paper is application of wave propagation with low strain pile integrity test, a case study. The speaker is J. Prakashwal from CSIR Structural Engineering Research Center, Chennai. Yeah. Please go ahead.
Good afternoon to all, sir. Myself Prakash Vel, working in Structural Engineering Research Center. Today I'm going to present about the pile integrity test we have carried out for a project. I also thank the conference coordinators and organizers for giving me opportunity for presenting our work here, sir. So this is the content of my presentation. Actually, the project has been carried out based on the requirement that the pile concrete has been carried out during the rainy season, and moreover the full length of the reinforcement has not been utilized. Hence, they asked us for evaluating the pile integrity. Here I have shown the common defects of the pile. And our objective of the study is to evaluate the integrity and depth of the piles. And pile integrity test is based on the pulse echo method. Here we give a small impulse with the handled hammer, and the wave passes through the pile medium and it gets reflected from the toe. And this is the basic principle of the pile integrity test. And this is the velocity of the wave in the concrete medium. And here we are measuring the pulse velocity of the pile concrete. Actually, pile integrity test results depends upon the velocity of the pulse velocity in the concrete. Hence, we measured the velocity also. pulse velocity also before going for pile integrity test. And here we are giving a small impulse over the pile top. Before going for pile integrity test, the pile top surface should be prepared well, sir. Because otherwise, if undulations are present, then ringing waves are will be shown, and this will not be, that will not be useful for us. And hence, pile surface should be prepared with the cement mortar or convex straw GP, and it should attain the sufficient strength to get the hammer impact. And here I have shown the different different wave we get depending upon the pile end conditions. Here this is a friction pile, there is no end bearing, hence the reflections are in the same direction. Here the pile is fixed in the rock, this is end bearing pile, hence the reflections come in the different directions. Again here the defect is intrusion, and here the defect is extrusion, and based on the defects and the end condition we get the reflections. And this is the typical plot, velocity plot, which we get from the pile integrity test. This is a normal pile. For a normal pile, generally we get a two reflection. Here this is due to the impulse, and the end due to the toe reflection. That is for the normal pile we get this reflection. And here due to some abnormality in the 7.5 meter and 12.5 meter, we get this reflection. Again here there is an abnormality at 7.5 meter. And our observation is we carried out the pile integrity test for 160 piles, out of which 101 piles we measured the depth of 23.4 meter, which is above 90% of the design depth. And for 10 piles it is below 23.4 meter. For 49 piles we could not get the toe reflections. And our main inference from the study is the soil stiffness, sir. Actually the pile itself is for the TG foundation for a power plant, hence it was very closely spaced. Moreover, the soil has been previously used for filling the fly ash from the nearby power plant, hence as a soil improvement measure they have used sand piles within the interval of 0.5 meter. Hence the soil has been stiffened. Due to the high soil stiffness, we could not get the toe reflections for the most of the piles, in addition to the non-uniformity in the piles. This is our acknowledgement. Thank you, sir.
Thank you. I have a few questions.
Yes, sir.
In all your graph which you are showing, the y-axis was different in all the graphs. So means it is very difficult to compare which graph is having defect, and because the things get magnified. So for future means you can have uniformity. So
Yes,
it
sir.
have a
Yes.
better understanding. So, and it is in normal practice also, means what the agencies does, they change the scale. So we will not be able to identify just by seeing the graph whether there is a defect or not. So scale is an important part.
Scale.
That is number one. And second means can you tell something about the limitations of this pile integrity test? Because most of the time we are not able to identify the defect. Whereas with other integrity test method like cross-hole sonic logging, we are clearly able to distinguish, yes, pile is having defect at these locations. So would you like to comment on it or say something?
Sir, I have one thing, sir. This is a purely qualitative test, sir. And moreover, depth also we can go up to, actually we tested up to 30 meters depth. That is the main this thing of this test. And we cannot quantify the defects.
Okay. Okay. So one more thing means where we have to do tapping from the hammer. Any guideline or any idea can you suggest? How many locations we have to tap and where we have to tap for one? Yeah.
Sir, actually we sampled 6 hits, 6 hits, and generally we used a center for tapping, sir. Near the center of the pile we used for tapping, sir. And for each pile we use 6 samples of hitting, sir.
Now the next SOP lecture, I'm inviting to the Professor Gianna Paulo Semularum, Polytechnical Tornio. Gian Paulo Semularum is currently Associate Professor at the Polytechnical di Torino. He has been recently visiting professor at the University of California, Berkeley, 2014-2016. He obtained his MS 2005 and PhD in 2008 from the University at Buffalo, Sunny in United States of America. Graduate come in Civil Engineering, University of Rome, La Sapienza 2001. He is the chair of the SHMMI Committee on the Resilient Structures and Infrastructure CORSI of the International Society for Structural Health Monitoring of Intelligent Infrastructures. He is also SHMIA Council member of the government body of the International Society for Structural Health Monitoring of Intelligent Infrastructures. He has been invited to 10 keynote lectures and 30 plus seminars worldwide. He has authored 73 journal papers and 192 conference papers, 17 book chapters, and 5 books. Sir research interests are community disaster resilience and sustainability to natural disasters. He has been awarded with a grant of 1.3 million euros by the European Research Council for the project Ideal Rescue ERC 2014 STG. He is editorial board member of the several ISA journals, Selector Awards, PIP Achievement Award for Young Engineers 2011, Seed Grant Award from the Civil Energy Institution of UC Berkeley 2015, Best Presentation Award in 2017 at SHMIA 8 Brisbane. So, with this, we are inviting to start to present his SOP lecture. Thank you, sir.
Okay, so first of all, I would like to thank you very much, all of you, for inviting me to this conference. I would have liked to come to India and for my second time and meet you all in person, but unfortunately, due to this pandemic situation worldwide, we cannot. However, I'm really enjoying the organization of this conference. I really like the format and the way it has been set up. So. Congratulations to you for this. So I also apologize because this presentation was supposed to be yesterday, but I messed up with the time zone in India and Italy, and so I asked to postpone to today. So that's where I am now. Okay, so good morning still, everybody. One moment. Okay, so as you mentioned in my CV, part of the research I'm going to show you today is part of a European project which started in 2015 and is a IRC grant. And through this grant, we were able to collaborate and start a deep collaboration also with the University of California, Berkeley, and in particular with one professor I would like to acknowledge because he passed away a few years ago, which was Professor Steve Main, and with the SIM Center, as well as with the Pacific Equation Engineering Research. So part of the research you will see, it's also work that I've done with my students while they were there in Berkeley. As I mentioned to you, this grant allowed me to develop at the Politecnico di Torino in our university a virtual reality lab in which basically we were able to use 3D printer as well as a movable shaking table that can be used to do some tests that you will see in this presentation, and also a supercomputer to do large-scale simulation. Now, the presentation outline is introducing the concept of resilience, and in particular, one of the framework that we deeply develop in collaboration with MCR, which is the people frameworks. And then I will show you some application to large-scale cities and how this can be also applied to developing countries, which is part of my current research nowadays. So resilience. Before we start, I just want to to show you this graph to show the tendency of the last 100 years, how the natural disaster increase worldwide in different continents, but there is always the same trend. And when we compare natural disaster towards man-made disasters, the ratio is 2 to 1. For example, this slide is not updated, but in 2016 we had about 600 600 natural disaster and 300 man-made. And this is the distribution of natural disaster divided by continent. As you can see here, the main component, the earthquake component, is in Asia. We are in Europe, and in Europe, actually, the main natural hazard are storms, as you can see, and flood. However, that small green line that you can see in the Europe belongs to mainly 3 countries, which is Italy, one of those. The second is Greece, and then Turkey. And I'm, as a matter of fact, I'm studying earthquakes. So part of the example and case studies that you will see are related to earthquakes. Now, this concept of resiliency, it's an old concept if we go back in the literature, and it comes not from our field, but from a psychology field, actually. Then it has been applied in engineering as the property of a material to bounce back. But recently, in the last few decades, I would say, the concept of resilience has been extended in civil engineering. The line here is showing me that I have only 5 minutes left. Is that right? Oh, okay.
No. You have 25 minutes more.
Okay. All right. So resilience, it's a well-known concept that has been spread worldwide. There are different programs in US, in Japan, New York. We have the 100 resilient cities with the Rockefeller centers and so on. But when we go back to the initial definition of resilience provided by Hemsier, is the area underneath this functionality curve, which we want to maximize. This concept is well known, so I will go kind of fast. And through this year, since 2003, that the famous paper of Bruno et al., this curve has been stretched up and down by different researchers, including plateau, step functions, if we look at residential buildings, and also including the aging effects, for example, or the coupling effect of different lengths in the same earthquake. Now, the main issue is how to measure resilience. So we have different type of indicators which can be classified according to the hazard, to the temporal, to the spatial scale. I will not go into the details, just to show you that there are many indicators, and there are also many approaches. Here probably is not completed this list, but I grouped mainly them in 2 main groups: the bottom-up approaches and the top-down approaches. Here in the bottom-up approaches, you can see a series of methodologies like the CART or the TRIV, and they are both can be either qualitative, quantitative, including all hazard or only few specific hazards and so on. And then we have top-down approaches. Even here we have the ICO framework for actions, the SPOR, which is the San Francisco Planning for Urban Research Association, the BRIC, which is another indicator from Susan Cutter, and at the end we have our model, which is the People Resilience Framework. And if we focus on the People Resilience Framework, basically this is a GIS approach, which consider each infrastructures or dimension as a layer. And these layers are 7 in the People Frameworks, and that can be combined. There are 2 ways to combine this information. One is a scenario-based approach, in which basically you are supposed to have an hybrid model of your community, where you have physical lifelines and non-physical lifelines. So you can model both infrastructure like water distribution, power distribution network, but also emergency authorities like search and rescue, first aid authorities, policemen, and so on. And once you have this huge model and you calibrate the model, you can then measure certain performance using the People Frameworks and compare this with certain performance level. If you're not satisfied with that, you can act on the 4R, which are robustness, rapidity, resourcefulness, and redundancy, in order to improve this resilience of the entire community, and then use this for designing. Of course, this process is quite complicated because it requires the model of your community. If you don't have that and you want to use in a simpler way the people framework, you can use an indicator-based approach in which basically these indicators for each one of the dimension components and subcomponents you can see here, you have a corresponding indicator because we identified something like more than 125 indicators, and we didn't want to reinvent the wheel, so we combined them using data from census. And by doing that, we show here a simple application to our country, in this case Italy, and we were selecting some of the indicators which belongs to the people framework, which we can find in our ISTAT. And by doing that, we will plot the chloroplat maps, of Italy. And as you can see here, there are a series of indicators, and by doing that, we could get the resilience of the emergency response of the reconstruction phase. As you can see here, some regions are more resilient to emergency response, in particular the central part of Italy, because they have more experience with respect to the northern part, which is the richest part, and so they have performed better in terms of reconstruction phase, for example. Now, all this information has been combined in a software, which, because we are at the end of the project, we are going to release it, so it will be public available. And in this software, we uploaded one community. The community that you're seeing here is the city of Turin. At least it's a resemble of the city of Turin, in which we implemented certain type of data that were available. And whenever these data were not available, we make up this data, in particular for the power and the gas network, which are sensitive information and we couldn't share. We have to make a reasonable network, which is probably compatible with the existing one. I will go quickly, and then with this model, for the first thing we did a large-scale simulation of what we call ideal city. This is a city of about 900,000 inhabitants, and with model all the critical infrastructure from the hydraulic network to the building. And I will go quickly about description of how we collect the data from the buildings. Basically, we collect information about the year of construction, geometrical data, and some additional information about the economy. All this information were taken from some website, from the City Hall, as well as from some European projects. And about also the topology approach. Most of the buildings in Turin are made of masonry. And as you can see here, we categorize them according to the technology, to the topology of buildings. Then we look also at the seismic zone. Through the years, the earthquake zone changed, and we look also at the resistance of the masonry panel according to the opening. So we define a sort of backbone curve, a capacity model, which we identify two capacity models, one for reinforced concrete and one for masonry. And we, through some energy approach, we were able to identify these 4 points of the curve. I will not go too much into the details. I will skip some of those slides about the methodology, but at the bottom you can see here there is a paper that now has been published, so you can have it if you are interested in the details. So by doing that, we apply the same concept also for the masonry by converting the panel of masonry in an equivalent concrete frame, and we were able to then model the multi-story building with an equivalent single degree of freedom non-linear system. And this is the Takeda model that we use to model each single buildings. And we implement all this in OpenSys version in Python, and we run some analysis. Here are some examples by using the supercomputer that we had in our research group. So we look at the speed, and we try to use ways to implement or to make the simulation faster. In particular, we try to use the GPU instead of the CPU, but there were some issues with OpenSys, and at the end, we decided not to use GPU, but to keep going using CPU. The main idea here is that we had something like 80 cores, to each core one single building, which was one single degree of freedom system, and then run the simulation, and then we assign, once the simulation is done, the new building to that. By doing that, we compare the results between GPU, CPU, and the multiprocessing techniques, and we figured it out that at the end the CPU for us was faster than the CPU single core, but also of the GPU. Here are some specific calculation looking at the ratio, and we figured it out that as the speed of simulation set up around the speed of 37, the number of buildings processed remains the same. These are some analysis, output of our analysis. It's an example of an earthquake. I think this one was at Centro, and we look only at one part of the city. And what we are plotting here is the top interstory drift, which is directly correlated to damage. So what we did, we did some tests assuming an epicenter in the southeast part of the city. And then we simulate 4 earthquakes, Centro, Pinoy, Kobe, North, 2 far field and 2 near field earthquakes. And we compare these results with the building archetypes and the area of construction. As you can see, in red is the downtown area, which is mainly ancient old masonry building. And when we ran our simulation, we figured out that the most vulnerable part was downtown, as expected. And far from the epicenter, we are low damage. And also the newest part of the city, which is in the south part, even if it was close to the epicenter, experienced low damage. So everything at the end was what as expected. Here are some results comparing the year of construction with damage data and so on. Now, the main issue, however, when we calculate downtime, when we calculate resilience, is how to estimate downtime. Now, we apply this concept of downtime to residential buildings in developing countries. But today, in this presentation, I will show you how we apply the same concept in developing countries. Because, as we know, most of the vulnerable countries are the ones that are developing, and because usually are mainly affected from natural and man-made hazards and poor quality of construction, and the fact that sometimes we don't apply any seismic design cause a lot of that. These type of buildings are here. I simply categorize them in adobe buildings, which are basically low energy buildings, which are fireproof and biodegradable. And they are perform actually pretty well against earthquake. Then we have the stone masonry buildings, which is a common type of building in rural areas. However, you need to provide certain retrofit techniques in order to perform well after doing earthquakes. And then we have bamboo buildings, which is green, biodegradable, and eco-friendly material, and is usually a good alternative for steel when steel is not available. And there are also prefabricated bamboo buildings and concrete surface ram and earth core buildings. Now, how do we estimate downtime for this type of buildings? So the main challenge is due to the fact that we have to deal with imprecision and uncertainties. Uncertainty that comes from the high numbers of involved parameters, by the accuracy of the available data that sometimes is not sufficient, and by the fact also that there are no models developed for this type of buildings in developing countries, and most of the time this downtime is affected by subjectivity and based on experience. So what we try to apply is a fuzzy logic approach to estimate the downtime for these buildings in developing country. The fuzzy logic, I will not spend too much time. I assume the fuzzy logic approach has been granted, but however, this methodology was developed by Zadeh in 1965 and is used to give or to quantify certain, sorry, one moment. Is used to quantify certain degree of uncertainties or certain measures that are qualitative only. And this is the scheme that we use. And basically, the methodology that we apply is based on estimating first the post-earthquake building evaluation using a rapid visual damage assessment. And then we build a building damageability model, which is based on a hierarchical rule, and through which we use inference to combine the indicators that come from the fuzzy logic. And then we finally estimate downtime combining three values of downtime: the downtime due to repairs, downtime due to delays, and downtime due to utilities disruption, which is the classification given by one professor in UC Berkeley. So in the post-earthquake building evaluation, basically this RVDR aims to analyze the damaged building and gather information of the building, design characteristics and components, and is used to also to describe the buildings. Then what happens is we have the building damageability model. Basically here in these figures, in this slide, it shows a scheme that show the two main components to the two main modules, which is the highlighted in gray, which is the site seismic hazard and the building vulnerability. The site seismic hazard basically get information mainly from the background of acceleration, and while the building vulnerability takes into account two aspects. One is the post-earthquake condition, and the other is the structural system. The structural system, it considers the type of floor, the type of roof, the type of construction, while the post-earthquake condition is related to the building condition right after an earthquake. If it's partially collapsed or completely collapsed, if the story are out of plumb or damage to specific structural members and so on. And this information are combined to get the building damageability. And then through these three columns, what you see up here, you will get basically the downtime due to repair, due to delays, and due to utility disruption. Now, to get this information about the downtime, we try to get the information of downtime taken from PACT, which is a software provided by the FEMA. It's a US Federal Emergency Management Agency. But this data were not good for developing countries. So we collect data from basically survey that we perform in some of the earthquake which happens in Nepal in 2015. And we combine them to get the downtime due to repairs. This is the repairs, and for each components, we can calculate for structure and structural components using the methodology, which is the same already, to calculate this downtime. And finally, we get this probability of non-exceedance and the downtime due to delays. And finally, we have also the downtime due to utility disruptions that can cause by being inoperative some of these power network or transportation network to delay all the process of the restoration. Somehow, to take into account the utility disruption, we use some fragility curves, which has been built based on earthquakes from collected from 1960 until nowadays, and our simplified approach, but it's the best that we could do with a simplified model. And then once we evaluate these three downtimes, we combine them to get the final downtime for developing countries. As I say, I applied this concept to the data we had in Nepal, and these are some characteristics of the earthquakes. You see, there were more than 500,000 buildings damaged and collapsed, and 9,000 people died. So we we focus only on residential buildings in this specific case, and here is the distribution of the type of residential buildings that were damaged and that were without missing information. So at the end, the number of buildings analyzed were 9,000, and as you see, of these 9,000, 38 were reinforced concrete, some were brick and mud, 37, and only a small percent were adobe, 2%, and so on. So with this database, basically, we look at the behaviors and the typical common failure for certain type of buildings. In particular, we focus on reinforced concrete buildings, so only one specific type. And the masonry building has some issue which are common also in Italy, which is the out-of-plane behavior, and also the fact of missing black box scattered box behaviors in the upper floor. And this is the results of our analysis, the building damageability calculations. As you can see here, while increasing the PGR, the number of damaged building increase, in particular in the medium damage level. And as you can see here. And here are some results related instead of the downtime estimations using the methodology I just described, which is based on fuzzy logic. As you can see here, for an earthquake with a PGR of 73G, the time needed to recover is more than, as you can see here, 4 years, and which is pretty much what is happening also nowadays. Okay, and then we have a series of measures to improve resilience in developing countries. So we can work on policy and regulation, some techniques like base isolation, low-cost bubble frame, confined masonry, low-cost housing system, and so on. Policy and regulation means also in implementing simple construction practice to reduce the risk of collapse, educate private owners, adopt approaches based on disaster risk regulations. For the base isolation, well, in developing countries, we can use recycled rubber fiber reinforced bearings, which can have a rectangular shape because that's more easier to be manufactured. Or we can use simply sand rubber foundation layer on which the structure should be designed to withstand the earthquake acceleration, for example. Low-cost bamboo frame are also applicable in specific cases. And then we have confined masonry walls. In this case, we can use steel and cement in India, for example, or we can use reinforced concrete element like tie columns and tie beams. And then we have also sort of low-cost seismic intervention, like arch foundation used in walls that are supported on brick or stone masonry, or filler slab roofing system when the after part of the slab is subjected to compressive forces, and so on. Well, so this is the part related to the developing countries. Now I want to conclude just showing some parts coming back in our project about what we did on the transportation network. We analyzed basically for the city of Turin, which we call ideal city, also the transportation network. We developed an efficiency matrix with more than 15,000 nodes, and we used two indicators: the average vertex degree as well as the efficiency, which is the shortest path between one node I and j, while we compare these results with 4 earthquakes, as you can see here: Northridge, El Centro, Cove, Aquinoa. Then we look at the interdependency. This is a picture we took in 2009 after L'Aquila earthquake, and you see the presence of debris due to the partial collapse of building make some of the roads unavailable. And these roads needs to be clean and available after an earthquake to allow the emergency rescue operation to act. So to do that, we decide to implement in a software which use the applied element method, the extension of the debris caused by the collapse of some of these buildings. This is one building that collapsed in Amatrice during 2016 earthquake. So we modeled this in this software, and we were able to calculate using a geometrical formula the footprint area of the debris caused by the complete collapse. And by using this with the debris area as you can see here in purple, we look if they intersect with the road or not, so that we can know in advance what are the roads that might or might not be available. Of course, this applies well only if they are full collapse. What happens is there is partial collapse. For partial collapse, we decide to use artificial intelligence. So using genetic algorithm, we were able in image detection to detect the extension of debris caused by the analysis of some specific pictures, as you can see here. And using this data and information, we were able to select some good picture with respect to the one that were not good by looking at 14 different earthquakes. And we compare these results by running our analysis, and we can see here what are the roads which were not available using this other approach. As you can see, Northridge, which is the near field, is the one where more damage. And then another aspect which is quite interesting and breakthrough in this project was the human behavior modeling during the emergency. Basically, no one so far ever modeled the panic effects and how this will affect on the emergency response. So we look at, by looking at some matrices, the memory, and take into account how the human behavior copes with dynamic changing environment. So basically, I will not go into the detail. For the paper you can see down there is the paper we wrote with Professor Main. We can look at the emotion, the memory, and belief, which are matrices which can be combined and calibrated using some surveys that we perform at UC Berkeley as well as at the Polytechnico di Torino with students. And then we were able to calibrate this panic model. Here is some application of mall which were located in Auckland, and the evacuation. And as you can see, these points are the agents which are moving out of the mall right after an earthquake through the emergency exit. And what we did, we learned our analysis with and without the human behavior model. And these are the results of the two curves. As you can see, if we don't consider the human behavior model, basically we end up underestimating the time of evacuation. We applied this concept not only to earthquakes, but also to blasts. There is another publication done in 2019, and we assuming that there were 2 blasts in the museum. And we look again at the emergency evacuation with and without the human behavior model. And this time the calibration was done with another type of surveys, but it worked well. However, we realized soon that these questionnaires were not good enough. We needed more unbiased evaluation, because everybody is it's a hero when he needs us to check a box, but in reality, maybe we will behave differently. So we decided to use some sensor to measure how is real reaction towards these dramatic or natural hazard events. But because we cannot experience an earthquake and collect this information, the only way is to use virtual reality. So what we did through a virtual reality mask vision of one of the scenarios that we were running to these people that were on a shaking table and were experiencing some of these shaking. And we were collecting biometrical parameters like the heartbeat, the respiration rate, and we were trying to collect data that we could be directly related to the panic. We made this during the research night in 2017 at the Polytechnico di Torino. We are going to repeat this experience now in September. After 4 years, finally the research night came back to the Polytechnico. This time we will do it at the Valentino Castle of the Polytechnico di Torino in September. And we will have more chance to get more data as well. So with this information, then we built an entire model, agent-based model of the city of Turin. And here are some initial preliminary visualization of these agents, which were running towards some shelters inside the building. But they found a roadblock, and so they decided to change the roads. Now, here is another view. And the interesting part of this, okay, you can see there are different colors. It depends on the state of injury of each single person. And what we see are the buildings which are different color according to the level of damage. Now, the interesting thing of this simulation is that through a virtual machine, we are also allowed to interact, so to be inside the simulation and interact with the simulation as well. So another project which we were involved, which was a side project with respect to the IDEAL rescue, is the IDEAL sensor project. In this project, we were analyzing the evacuation due to fire in a school building, which is located in Melzo, near the Milan. And here we built a BIM model of in Unity of the entire school. This is some view of this simulation model. We collaborate with the computer science research group of our university, and we did some analysis simulating the smoke propagation using FDS. Here are some simple examples of how to propagate and how we could transfer the information from FDS directly into Unity to run our simulations. And here is the steps that we follow to move from one software to another one. And finally, just to show you the final results, it's the smoke propagation that we can see inside the Unity model. So with this, we built virtual reality training platform for rescuers. Here it's our platform in our department, and here is the school. Basically, the test was entering inside the school, which is fire, looking at the map of the school, and then get through the stairs and reach the person which were injured, and then bring them back to the rescue point. So what we were doing, we were measuring basically the time needed to perform all these simulations. And we're going to repeat this experience also in September during the research with the same application. As you can see, this is exactly, I've been in that school, so it's exactly the same. They made a good job in actually representing the school the way it was. And basically they enter in the room with fires and they find the person injured on the left, and then they try to collect them and bring them out. Okay, I think I have not enough time to show you everything, so let me move a little bit faster to the monitoring part. Now, when we're talking about monitoring, because it's one of the research of our group, we look at two types of monitoring. Monitoring smart cities, which is something that you've seen, monitoring infrastructure, and monitoring people. So if we look at smart cities, we can use Internet of Things, as you've seen some examples here. When we look at the infrastructures, nowadays this is a very sensitive topic in Italy, because as you know, a few years ago, one famous bridges by Professor Morandi collapsed, and we were able to rebuild quite quickly, I would say, for Italy. And however, we studied this collapse using the software I mentioned you before, because we are collaborating with I.I.Sc, and we published this paper in Engineering Structures. And so here, basically, this collapse is now very clear that was due to the lack of maintenance. And so nowadays there is a big research project on monitoring bridges and tunnel to see how they perform and how they are aging through times. And here are some curve that proves how the investment costs in maintenance after the bridge became private in 1992 dropped significantly, and basically it was indirectly the cause of collapse. Now, this is for infrastructures. Let's go instead how you monitoring people. Now, we have a project which is called Ideal Sensor, and now it's called Ideal Drone. It's the second follow-up project in which basically we're trying to monitoring the position of people inside buildings which are in emergency or need search and rescue operation. So in order to optimize the search and rescue operation of firefighters, which usually are involved in death during their operation because they are not aware of the building where they are entering and the risk that they are facing. So with this system, our idea is to let them know the position of the people who are in danger, their health condition, by knowing or transferring to the outside of the building the body parameters like temperature, heartbeat, and so on. The combination of this information will allow us to know if the person is injured, dead, or is in healthy condition. And so basically you imagine that if you are a firefighter, you're outside the building, you have a map of your floor in which in green are the people in normal condition, yellow the people which are injured, and red are the dead people. So basically first responder, which are in blue, can then optimize the search and rescue operation and moves towards the people who are injured or are in health condition so they can move them out and skip for now the people that are dead. So we implemented a series of anchors and tags to develop this technology. And here are some prototypes of this system. We made a test at the Polytechnic di Torino and patented the system. This is the final watch we use it. And this is the software to transfer the information from outside the building towards the outside. And this project has been also, we applied for extra funding by including also new technology, exoskeleton and augmented reality. Unfortunately, it wasn't funded last years, and there was also this issue of the COVID-19. So we are planning to reapply now with the new program, Horizon 2020. And in this project, we are involved also with some research group from South Korea, from I.I.Sc, in particular for the use of the exoskeleton. And with this, thank you very much for your attention. I will be happy to answer any questions. And most of the things you've seen are in these papers and in this book related to resilience. Thank you.
Thank you, Professor.
Hi, can you hear me? Yes.
Yeah, it was a very nice presentation, and I can say in just 30 minutes, we all can imagine, means from starting the how disastrous the earthquake can be and how it can be managed, means the earthquake incidences in a very systematic manner. This first time we are all the things, all the parts we are seeing in one platform. in just 30 minutes. So it is very good session, I can say, and it is we improved our knowledge and understanding about earthquake management and mitigating not only the risk and but also the minimizing the damages also. I think Professor Ramna will tell further. Means
I think there is one question.
Yes.
And I
Yes,
think
sir,
that is for some other person. That is not for him. Not for him. Okay.
no, in your simulation, did you model building during Giano and Palazzo del Lavoro designed by Nervi? There is a question. In your simulation, did you model the buildings Torino Esquigiano and Palazzo del Lavoro designed by Nervi?
Okay, one moment. Yes, maybe I can hear you well better with this. Can you hear me?
Yeah, we can hear you.
Okay. Yes, we model the buildings, of course, because we are. I didn't mention we are talking something like 26,000 buildings, so we cannot go too much in detail. Okay, otherwise we will be running simulation for days, and this is not the purpose of this simulation. The idea is to develop a software or a tools that can be used to assist during the emergency the people, so that they have an idea which are the roads which are available, which are not available. So the information should be given quickly, in few hours, not in days. Okay, so the simulation needs to be fast. So first of all, of course, supercomputer help you, but also there is a limit from supercomputer. So you need definitely use a simplified model. So we used to say, I used to teach, in seismic engineering, that sometimes you don't need a Ferrari if you just need to reach, the bar which is downstairs, and so you can use your 500 Fiat. Okay, so in that sense, sometimes simplified model works well for what you need to do, and so we model each building with a nonlinear but single degree of freedom system, and we obtain this model from a multi-degree of freedom systems. So we made an equivalent transformation. It's something similar to the, I'm sure you're familiar with the pushover method of Professor Fiver, the N2 method, or CSM. So we try to simplify to run large-scale analysis. However, okay, one of my colleagues that is closer to my research and did something similar is Professor Shinsen Lu from Tsinghua University. He is doing the same model for Beijing, but he's applying a multi-degree of freedom system when he looks at the tall buildings, because there are many tall buildings in Beijing. So he's using a slightly different approach, but this is not our case, because most of the buildings in Turin are 4 to 5 stories, so it's pretty flat. So, but yeah, I mean, this is our approach. There are many ways, many groups that are working on large-scale simulation that use different ways to get to the same point. I don't know if I answer your question.
Ramana?
Sir. Okay, sir. Actually, thank you very much, and especially this session is very good. And total two SOPs. One is, I think, the eminent professor Geethankar Chaudhary sir has given an excellent lecture. Especially, we learned many things, not only for me, and all maybe participants also. They may gain a lot of knowledge in the area of especially the peak particle velocity and how the uncontrolled ground-borne vibrations, design of substructure systems. So theory, practice, and moreover, actually, Sarah has explained especially how the IS codes and the other Euro codes actually has to be implemented while doing the numerical modeling and at the time of characterization. Especially, Sarah has given excellent case studies of 2 cases for especially heritage structures as well as metro train track, and I think it is very useful for this particular information for all the participants as well as the practice engineers. And another SOP lecture by Professor Gian Polo Samloro sir. This is a civil engineering approach to elevate and manage resilience against natural disasters in developing countries. I think we have to learn many things from this. I think first time I've seen one of the earthquake. I think we can predict that one and assess those things in a numerical modeling and reality also. And it is very useful for all the earthquake and the dynamic soil dynamics profession. So in addition to that, there is a three presentations they have presented. The number one is numerical studies of dynamic loading on ballast railway track by the one is Panjal Mandani and from the Indian Institute of Technology. And this is especially at present days, I think Indian railways, they are actually looking for the new technology for the construction of railway tracks. So without ballast, it is very useful that one. And I think that topic is good for in respect of dissemination of knowledge to the entire research fraternity. And another one is actually that is analysis of urban planning under different loading conditions. That is especially for soft and weathered rock. I think the rock itself lot of uncertainty. So I think with consideration of that uncertainty, if they will go forward direction, I think this is very useful, especially for the tunneling of nowadays. Actually, there is a need of tunneling system. So and they are presented. That is also one of the useful lecture presentation. And the last presentation, one more actually was given a case study by J. Prakash sir. That is regarding the application of wave propagation with the low strain oil integrity test. So this is also very useful and good presentation. So and moreover, I thanks to the especially organizing committee for giving this opportunity, and also I thanks to my actually my thanks to the Dr. R.P. Singh sir. In the morning onwards, actually he has guided properly. You have to come at the right time, and also I extend my thanks to especially Ravijakka sir and Raghuveer sir also. I think 2 days before also he has given certain guidelines what we have to do in this session. Thank you very much for all the participants as well as for the SOP professors also. Thank you very much, sir.
Thank you. So we are at the end of the session. On behalf of the organizing committee, I thank all the speakers and the chair and co-chair for effectively conducting the session. We are very much thankful to Professor Simarello, though he could not make it for making it today. And we learned a lot about his simulations. Very good, very interesting thing we could learn. Thank you very much. Thank you all. So now we'll adjourn and rejoin for the session, plenary session at 2 o'clock. Thank you. Thank you all. Thank you very much.
Thank you.